So today is a very important class from the point of view of scattering. Although we will just try to derive all this thing, and it is very difficult to derive a scattering equation, but I tried it my best. Let's see how this whole theory is evolving. Because unless until you will not understand theory, you will only mug up the equation, and finally you will confuse into the exam that which formula you have to use and which method you have to use in the examination. So today's class we will just give the theory. Mainly first theory is the partial wave theory, and we will see how difficult is this particular mathematical theory. Then we will try to formulate Born approximation, which is really very smart way to calculating the differential scattering cross section. And then we can also discuss what are the basic physics, what is happening inside this particular system. It's a very interesting if you just uh, try to learn how this particular mathematical formulation of quantum mechanics evolve. So let's go from last class. So I think we have remember that we stop at this particular point, that we have equation d square u upon dr square minus L into L plus 1 r square u is equal to nothing but minus k square u. And what is solution of this equation? The solution of this equation is ur can be written as sum a, and you can put al also, so there is not any problem. A r and jl kr, and plus you have br nl kr, and this jl and nl are the spherical Bessel function, and which has somehow a function of sine and cos. Let me give you some basic example of these two functions. For example, you can have j0, L is equal to 0. So obviously we know L will go from 0 to all positive number, all positive integer. So J0 is nothing but you can have sine x by x. Similarly, J1 is equivalent to, you can write sine x by x square minus cos x by x. Similarly, we have NL also. So I can go for N0, and N0 is nothing but minus cos x by x. And we have N1 is obviously minus cos x x square minus sin x x. So these are the function. You can have similarly J2, J3, all are very complicated function, but yes, they are function of sine and cos, and also we have some algebraic function. So these are the spherical Bessel's function. But we want to write all the story in term of exponential function. And so because we know that at r tends to is at the bigger r, what we have basically a free particle, and this is a spherical in nature. So why we need to write each and everything in this form? So why we will use a new type of function that is known as what? Hankel function. So let's see what is this particular Hankel function. So Hankel function, I can write something, two type of Hankel function. First is HL, one type of Hankel function, and this is known as Hankel function. Okay, Hankel's function. So आप जैसे जैसे क्वांटम मैकेनिक्स में आगे बढ़ते जाएंगे, वैसे वैसे आपको डिफरेंट टाइप के फंक्शंस मिलते जाएंगे, है ना? एंड यू हैव टू लर्न हाउ टू वर्क विद दिस फंक्शन. So obviously this is your Hankel's function, and this can be written as, suppose it is function of x, then jlx plus I nlx. So this is type 1 Hankel function, and similarly HL2x बताओ तो ये क्या होगा? What will be type 2 Hankel function? Obviously JLX minus I NLX. So these are the Hankel function. And what we are going to do, and what is the property of Hankel function? So the property of Hankel function is very interesting. And why we are taking this thing in account when we have HL1 type Hankel function, let's say this is function of X, then it has property of minus I to the power L plus 1, and it has e to the power ix by x when x is very greater than 1. And similarly, you have second type Hankel function HL2x. It has also property that I to the power L plus 1 e to the power minus ix upon x, x is greater than 1. So now these are the property of our Hankel function for the very large x. This is for the very large x. So you can see. Now can you please tell me if I can write this thing as a function of Hankel function, I can write this thing also as a function of Hankel function, but when we see the whole physics, what is going to happen? The plane wave is coming. This is my incoming plane wave. And a scattered wave is something a spherical wave and which is going outward direction. So this is just going outward direction. So out of these two Hankel function, which function you are going to accept as a physical solution of my scattering?
The second one.
Second one या first one? ध्यान से. What is this? This will tell you what is scattering. The something is coming and it is going into same direction, isn't it? So if incoming particle is e to the power I kz, then what will be a scattered particle? At the r tends to at r is very big. जब बहुत बड़ा हो रहा है तो क्या होगा? What will be that function? Is that this one or this one? Obviously first one.
First one.
Obviously first one. Because you have something, which type of solution you have? You have very nice solution. Look at your solution for the scattered wave. It's something a e to the power I kz plus f theta e to the power I kr by r, isn't it? This type of solution you needed. Our main target is that I have to calculate this f theta. So if this is my general solution. So if we are doing a lot of calculation and we just want to write this particular function, then obviously which type of Hankel function is going to match this one for this particular equation? Type 1, obviously, isn't it? Because here is plus x plus ix is there. So we have to take the solution which will be type 1 Hankel function, because it will just behave like this particular function. It will just behave like this particular function at the very bigger value of r. Yes? Comfortable up to this?
Yes, sir.
है ना? So let's try to write the complete solution, and obviously we have done little bit, and obviously for given value of L there are 2L plus 1 number of functions are possible. And obviously we we have ylm theta phi is also a solution, because we have a spherical symmetric potential here. So what is the general solution? I am just writing the final general solution when my potential is not equal to 0 and we have centrifugal term. So the solution is basically, we can write my solution as psi as a function of r and theta, and this value is a, and you have e to the power I kz plus k is the same root under 2m e upon h cut square this is wave vector, summation over L is equal to 0 to all possible thing I to the power L plus 1 and this is due to degeneracy 2L plus 1 and we have, let's say, AL is some amplitude. Some amplitude, I am just writing AL. I don't know what is AL. I have to calculate what is this particular AL. This is the real challenge. And we have our solution as HL1 type solution, KR, and obviously this value is going to, this value will be obviously PL cos theta, and this is nothing due to this particular angular symmetry of a system, PL cos theta. We can avoid YLM part, M part we can avoid, we have the spherical symmetry. So this is PL cos theta. So this is our general solution. And what is property of this Hankel solution? Property of this Hankel solution is that this particular solution will be e to the power I kr upon r minus I to the power L. Isn't it? When we have kr is very, very greater than 1. Obviously, this will be k. Okay? Are you people going to understand this thing?
सर ये इक्वेशन जो हमने एक्सप्रेशन लिखा है ये हमारा जो वेव फंक्शन हमने पिछली क्लास में लिखा था e to the power I k z plus f theta e to the I k r by r.
Yes, that is the exact total. Incoming wave plus a scattered wave. This is equivalent to actually a e to the power I k z plus f theta e to the power I k r upon r. Okay? These two are same thing.
तो सर हमने जो ऊपर वाला एक्सप्रेशन लिखा है वो कैसे लिखा है, मतलब हैंकेल फंक्शन के टर्म्स में?
अभी तो सॉल्व किया ना, अभी तो सॉल्व किया इस इक्वेशन को, डी स्क्वायर यू अपॉन डी आर स्क्वायर माइनस एल एल प्लस 1 एच कट स्क्वायर यू इज इक्वल टू माइनस के स्क्वायर यू. अभी सॉल्व किया ना इसका सॉल्यूशन लिखा कि नहीं?
यस सर.
एनएल और जेएल के टर्म में और उसे हैंकेल फंक्शन के टर्म में लिख सकते हैं, ये तो लिखा ना?
यस सर.
हाँ, और जब वो लिखा तो हमको मुझे कुछ फिजिक्स तो इंट्रोड्यूस करना पड़ेगा कि नहीं करना पड़ेगा?
यस सर.
हमें बाउंड्री वैल्यू लेनी पड़ेगी ना?
यस सर.
सो बाउंड्री वैल्यू में हमें हैंकेल फंक्शन, टाइप 1 हैंकेल फंक्शन विल बी द आंसर, will be the solution. This is just a general solution. We don't know what is this f theta, but this is mathematical solution, isn't it?
Yes, sir.
Are you getting this thing? This is after solving the Schrodinger wave equation when you have v is equal to 0. Are you getting my point?
Yes, sir.
This is my solution when v is equal to 0. And yes, this is again some unknown thing. I don't know what is this AL, but this thing can be identified as amplitude of partial wave. What you are doing? You are just taking superposition of all possible waves in the outgoing function. Are you getting my point? This is nothing but the superposition, isn't it?
Yes, sir.
Because L is there. But beautiful part of this HL1KR is that this function will behave like this one. So why we have taken this as my solution? And obviously this is due to basically your degeneracy part will come here, and PL cos theta is the obvious solution when your potential is spherically symmetric. So I have written the complete solution with some unknown AL. Are you getting my point?
Yes, sir.
Hannah? So we have this particular thing. Now, if we are going to compare this thing, then we can get the value of f theta. So let's see what is my value of f theta.
और सर H1L KR में minus I to the power L plus 1 होगा ना?
Minus I to the power?
L
plus 1. That will be L plus 1. Sorry. This will be L plus 1. So it will much better that ये दोनों एक दूसरे को cancel कर देंगे, है ना? Minus L plus 1. So now, what is this f theta? So I can write this f theta, and look at this f theta. When I will write this f theta, you will surprise, this is not just a one number, but rather it is a superposition of different type of amplitude. Are you getting my point? Look at this particular f theta. Just try to write this particular thing. We are just writing HL1 KR as this function. And then what is my f theta? My f theta is basically summation over 2L plus 1 AL PL cos theta. This is my some value of f theta, isn't it? If we are going to compare these two things, this k and this k is going to cancel out. I am just going to compare the coefficient of e to the power ikr on there, and I have this particular thing. Now, what will be f star theta? That is complex conjugate. And this value I can write with the different indices. I will just tell you why I am taking different indices. 2L dash plus 1, AL dash, PL dash, cos theta. Okay. So this is your f star theta. Now, what is your differential scattering cross section? This is mod f theta square, isn't it?
Yes, sir.
We have seen in the last class. The differential scattering cross section is nothing but mod f theta square. So let's try to go for this. यहाँ तक clear है ना?
Yes, sir.
देखो इसके ऊपर प्रॉब्लम आए थे, इसी कारण मुझे ये करवाना पड़ रहा है ना? In 1 year there is problem based on this particular thing, and the calculation is exactly same thing. Look at here. What is this particular problem? And what is value of L? L is equal to 0, 1, 2. So this is nothing but one type of superposition, isn't it?
Yes,
And
Yes,
you
sir.
remember from the interference and all kind of thing is a superposition, and you are getting the same type of solution. Just wait little bit, wait for the 2 minutes. Now I have d theta, and this d theta square is nothing but f star theta and f theta, which is equivalent to what? Mod f theta. Okay. Now, if I will take both have same index, then what will happen? Only multiplication of 1 1 will be there, 2 2 will be there, 3 3 will be there, isn't it? If I will take this L dash will be same as L, then if I am going to multiply, then what will happen? Only diagonal term will be there, isn't it?
Yes, sir.
yes, sir.
But we want all possible superposition. We want superposition between 1 and 2, 2 and 3, 1 and 3. Then what we have to do? We have to write this as a different indices. Are you people going to understand this thing? Why we are taking this thing? So here we have double summation, not single summation. So what is this double summation? The double summation we have L dash as well as L, and both will go from 0 to infinity. And this value is basically 2L dash plus 1, 2L plus 1, and obviously this is a star. Okay. So here AL star dash AL, and we have PL dash cos theta, PL cos theta. Now look at this thing. This is your differential scattering cross section. Please, this is your differential scattering cross section. And what is value of? So here we are taking all the possible combination. All possible combination we are taking here. 1 1, 1 2, 2 3, 3 3, 3 1, 3 0. All possible combination is there. Suppose I am going up to 3 term, then how many term will be there? Then how many term will be there if I am just expanding up to third term?
9.
9 term will be there. So you have to always keep in mind that there still will be 9 term. But I am more interested not only calculating the d theta square. This is d theta. Sorry. I am just want to calculate the total scattering cross section. When we are going to write the total scattering cross section, then look at how this thing will be compact. So sigma is total scattering cross section, and this will be d theta sine theta d theta d phi. This is my total scattering cross section. And when we are going for this, then obviously I have summation over, and this is double summation L dash 2L dash plus 1, 2L plus 1, and here we have AL star, AL star dash AL, and we have integration of PL dash cos theta, PL cos theta, sin theta, and this will be from 0 to pi, and d phi is nothing but 2 pi. Okay, d phi will nothing but 2 pi. Now, can you please tell me, and d theta is also there, what will be this integral? I think you have done this integral many times in your
Multi.
lot of places, in multiple expansion, in quantum mechanics, algebraic thing, as well as your legendary polynomial. What is this particular integral? Please have a mathematical brain. Hai what is this particular integral? This integral is nothing but 2 upon 2L plus 1 delta L dash. This is nothing but the orthonormal relationship, isn't it? याद है?
Yes, sir.
Yes, sir.
आलोक सर ने करवाया होगा इसे, है ना? So this is this particular integral, and when now this sigma will survive only for L is equal to L dash, isn't it? Because
Yes.
this is nothing but the Kronecker delta, and only it will survive for L is equal to L dash, and 1 2L plus 1 and 1 2L plus 1 will be cancelled. This 2 pi will be go there, and this double summation will convert to the single summation, and we have basically 4 pi summation over 2L plus 1 mod AL square, and this is my total scattering cross section. If I am able to calculate AL, again challenge is always there. If I am able to calculate this particular AL, I can write what will be my total scattering cross section. So let's try to go for how we can calculate this particular AL. Obviously the boundary condition will be very useful, but if you have complicated situation, then it is not going to work. It is absolutely very tough to calculating this particular AL. But yes, in somehow, in some sense, we can easily calculate this particular AL. Up to that, are you people comfortable?
Yes, sir.
एंड एग्जाम में क्या आया था? एग्जाम में डी थीटा उन्होंने दे दिया था, and basically they have given f theta as some this function, and they will just give you 1 and 0 के लिए दिया था इन्होंने, and they just want for which this will be maximum, for which what will, if this will be maximum, what should be the condition. तो उसके लिए क्या करना पड़ेगा? d theta upon d theta is equal to what? 0 को यूज करके आप फिर मैक्सिमम मिनिमम का कंडीशन लगा सकते हो. So there was one problem in exam. We will try to do this thing, but before that let's complete, at least today we will complete our all theory. कल से हम लोग सिर्फ प्रॉब्लम ही करेंगे. Okay, up to that everyone is comfortable?
Yes.
Let's try to go for one problem such that you can feel how difficult to solve this type of problem. Okay. Now look at, we have to play a trick when we are going to solve this thing. What we have basically e to the power I kz. This is my incoming wave. Now, in the spherical polar coordinate, we can write e to the power I k r cos theta. लिख सकते हैं ना?
Yes, sir.
Yes. And this thing can be also written as a summation of series. And this will be something I to the power L 2L plus 1. And this will be basically JL KR PL cos theta. You can write this particular expression as this particular series. Okay, so you can remember this particular thing, because just you can go for the Taylor expansion and you can write in a, if you can take all this thing, all possible, just you can equate all the coefficient, then you can write in this form also. है ना? You can have cos theta 1 plus cos theta square term. So you can any polar angle you can write in a basis of basically PL cos theta, any function of theta, isn't it? You have to do some exercise, but you can write. This is basically the thing we are just using. And yes, this is function of, hence KR is also there. Then this will be the radial part of solution. And we know why we are taking this particular solution, because this solution is where we have potential is equal to 0, isn't it? When your potential is equal to 0, then obviously the solution can be equal to JL KR as well as NL KR. So we have accepted JL KR as my solution. So what is my F theta? Sorry, psi R theta. So e to the power I kz, I can write as summation over I to the power L 2L plus 1 JL KR PL cos theta plus, and the scattered part is all about, what is this scattered part? क्या था यहाँ पर? That will be, sorry. So this will be I to the power L plus 1 and yes, sorry, this will be summation over K is there, and I to the power L plus 1 2L plus 1, and we have H L KR and we have PL cos theta. This is e to the power IZ, and this is all about, and we have also AL also, है ना? AL also is the solution. And okay, this is HL, one type Hankel function you have to take. Okay, so we can take a lot of things common here, isn't it? क्या क्या common ले सकते हैं? I can take a summation over L I to the power L 2L plus 1. I can take common, as well as we have JL plus I AL HL1 KR, and we have PL cos theta. So this is my complete solution in term of only R and theta. We just avoid Z part also. So this is the complete solution. We have make a trick. Now we can just try to solve one problem. What is my potential? This is hard sphere. So potential is equal to 0 if we have R is greater than A, and infinity if R is less than A. Then we have to calculate the total scattering cross section. Can I solve this thing? We have to calculate the total scattering cross section. So this will be R. So what will happen when R is less than A? What is your wave function?
0.
0. Because you have potential as infinite. This is something, this kind of potential is there. This is A. and this is infinite potential. So this is typically infinite, very hard sphere. You are just sending the particle from here or from here, and we have this particular thing. Now, what will be solution? R is greater than A. The potential is 0. So what will be solution? R is greater than A.
The spherical wave.
This one, the solution, isn't it?
Yes,
This
sir.
solution is for what?
V equals to 0.
V is equal to 0. So this is my solution. Obviously, this is incoming wave plus a scattered wave. Then the superposition of incoming plus a scattered is my solution. So this is my solution for R is greater than A. And this is solution for R is less than A. Now what we have to do? We can use boundary condition, isn't it? What is my ultimate aim? My ultimate aim is I have to find what is my AL. So we have to use boundary condition. So what is boundary condition here?
That psi of k should be continuous.
Obviously, we have basically psi a theta must be equal to 0, isn't it?
Yes,
This
sir.
is my boundary condition. So when we are putting this particular boundary condition, then we have, this is nothing to do with here, we have JL KA and one K will be also there, I think, है ना? एक K छूट गया यहाँ पर. So we have K is there. याद रखिएगा, please. First equation में K भी है ना? Last में, just check it. So one K will be also there. So JLKA must be equal to, sorry, JLKA plus IKAL HL1 KA must be equal to 0. So what is AL? AL is equal to, what is AL? I can calculate AL, है ना? So AL is equal to minus JLKA upon IK HL1 KA. Okay, this is your AL, and you can find all this possible, and these are known function. Don't worry, these are known function. All possible AL. You are just going to compare L is equal to 1, L is equal to 0, L is equal to 2, everything you can calculate. You can calculate all the amplitude, all the possible amplitude, starting from 0, 1, 2, 3, they are just making superposition, and they are just giving you the what are the possible amplitude. So what will be my total scattering cross section? What will be my total scattering cross section? So sigma is equal to 4 pi summation over 2L plus 1 AL mod square. So what will happen? The answer will be 4 pi K square, and here you have 2L plus 1, and you can JL KA upon HL1 KA mod square, and you can find all possible values. Yes, this is your answer. You cannot do anything about this unless until you have another approximation that when K is greater up to L is large, then what you can have. But this is your general solution, and you can write this answer. Yes, in the examination they can just give you that write down this value up to L is equal to 1, L is equal to 0, and if they give this, but if you know this particular function, you can easily write this thing. So this is your solution. So can you feel the complexity behind the solving the problem? And
Yes.
this is problem where you have a very nice kind of situation. Please, here my potential is infinite, less than A. What will happen when potential is some finite and constant value? This is the simplest thing, but we are not able to solve this particular problem from here. So this will create a havoc. And if your potential is something like e to the power minus alpha r by r, then obviously it will create huge problem. So it is the scattering, the complete solution of a scattering is not so simple. But yes, somehow we can guess the solution. Somehow we can make a trick such that at least we can formulate the solution when your potential is equal to 0. Are you getting my point? But
Yes,
if
sir.
your potential is not 0, how you will approach the problem? Obviously, this is going to fail, isn't it?
Yes, sir.
है ना? Feeling difficult?
Yes, sir.
If you are not feeling difficult, it's a bad thing. Okay? This is difficult thing. And this is real challenge for all of us, that we should go for a nice solution, such that we cannot go for the generalized solution for something like Schrodinger wave equation. And even Schrodinger wave equation, up to harmonic oscillator, we can only solve the thing. But after that, it is very difficult. So this is real problem in quantum mechanics, that how you will get the generalized solution. It is very difficult to get the generalized solution. So why we have approximation method, so why we have degenerate, we have perturbation, variational principle, WKV approximation, to at least we can approximate our solution. And similarly, here we have very smart approximation method that is known as Born approximation. And that Born approximation is at least approximated up to somehow that at least you can first order approximation, you can give the nice solution, you can analyze all possible potential which can be integrable in a nature. So let's go for the formulation of Born approximation. किया जाए उसे?
Yes, sir.
Yes, sir. Yes, sir.
टफ लग रहा है, बट इसमें मैं कुछ नहीं कर सकता हूं. Nobody can do anything, but at least you can learn what we are going to do. हम क्या कर रहे हैं, कैसे सॉल्यूशन की एक्सेप्टेंस है, क्या हो रहा है हमारी चीजों को, ये सारा हमें देखने की जरूरत है. लेट्स गो फॉर बॉन्ड अप्रोक्सीमेशन. इट्स अ very interesting. Okay. And very few people will do this derivation. People usually start from the formula, but I like to do this derivation because it's a very interesting. And every time I learn something new when I am just going to do this particular derivation of Born approximation. So let's see how all these concept of green function and all these thing will come into picture. So I think you have time now. So कितना time हो रहा है? Yes, it will take hardly 15 minutes. So we will finish it. ताकि next class में हम सिर्फ problem कर सकें. Okay. Now, what we have seen in the partial wave analysis. You have seen in the partial wave analysis that we can solve the potential when it is 0. But in general, my potential is not 0. When this comes, then obviously we have to go for different method. So let's try to learn Born approximation. So we have Schrodinger wave equation minus h cut square upon 2m del square psi plus v psi is equal to e psi. Okay. So this is our Schrodinger wave equation, and I have to solve this particular Schrodinger wave equation, isn't it? And in general, we have, so how we can solve it? We can just write this particular thing, del square psi minus 2mv h, and v can be function of r and theta, don't worry. So 2mv h square psi is equal to minus 2me upon h cut square psi. What I am doing, I am taking this thing here and this part is there. So we have del square psi plus 2me upon h cut square psi is equal to 2mv upon h cut square psi. We can write del square plus this thing is something like k square, and this k is, I just write this k as a small k. Okay, there are n number of k will come into calculation psi, and I am just putting this whole thing as q, and in this q we have one function psi also. Okay, this is my one function psi, and this equation is very famous equation known as Helmholtz equation. Helmholtz equation. Our real challenge is to solve this equation. In general, it is very difficult to solve. And yes, please remember this q have 2mv h cut square psi. Psi is there. So this is inhomogeneous equation actually. Not homogeneous. So how you can solve this type of equation? So what you will do, you will solve this type of equation with the help of green function. है ना? So you can just find one particular function del square plus k square, and let's say this green function is gr, and here we are writing in a vector form. What is meaning of this vector form? Means r theta phi. Are you getting my point?
Yes, sir.
है ना? जब मैं वेक्टर दे रहा हूं तो r theta phi लिख रहा है. And if this function have something del cube, and basically you have Dirac delta of r of cubical, because this is in the volume. So if we are going to solve this equation and we find this particular g, then obviously the solution for psi can be written as, the solution for psi can be written as some integration green function r minus r naught, and this is function of r actually. So I have taken some r naught. I will discuss what is this r naught, and we have g r naught and q, this value is q r naught and dq r naught. What is meaning of that? Why we have taken r naught here? Because if you will do the integration in term of r naught, you will get r outside, and we need some psi r. Are you getting my point? So the real challenge is that what will be this particular green function, and when we go to solve this particular differential equation, I am not going to solve this particular differential equation, then we find or take our green function as gr as some very interesting function, and obviously we have also intuition that my wave function will just something like a spherical in nature. So that green function is identified as minus e to the power I kr upon 4 pi r. This is my accepted green function which will satisfy this equation. And you know that del square 1 by r is nothing but del cube r. ये आपको पता होगा, है ना? You have this particular information, na? What will happen? Del square to the power 1 upon r.
Del cube
Del cube r, del Dirac delta function. So why we have just accepted this as my green function is my solution. So we have this particular solution. So this is my exact solution we can find. And now look at what we are going to do here. Are you people comfortable up to this?
Yes, sir.
Okay. और ये इक्वेशन कैसे सॉल्व होता है? इफ यू वांट आई विल टेल आलोक सर दैट ही विल गिव यू द कंप्लीट सॉल्यूशन जस्ट यूजिंग lot of contour integration and all this thing you can find up to this one. This is well known solution, so don't worry about this. This is solvable. Now what is my wave function? So my wave function is incoming wave. Let's say this is some psi r naught minus, here we can write q r naught in a function of v r naught. लिख सकते हैं ना? What is q r naught? q r naught क्या था? 2mv upon h cut square, and obviously this is function of r as well as you have psi as a function of r. This is function of q r, so you can put q r naught there. So obviously we can take 2m upon h cut square outside, and we have minus 2m upon h cut square. Why this minus? Due to this one. So we have integration of e to the power I k r minus r naught upon r minus r naught, and we have v r naught. This is due to q r naught, and I am just removing this particular thing. And this value is equal to d cube r naught. Sorry, psi r naught is also there. Psi r naught is also there, and we have d cube r naught. So actually, this is our complete solution. Okay, what is this r naught? Look at, in general, our potential is basically short range potential. So this r naught is inside this particular region. This is your r naught, and this is your r, and this is your r naught, and this is your r minus r naught vector. Okay, so this kind of situation is there. We are finding the solution at this particular point, and we are watching the effect of this potential here because we have potential here. Are you people comfortable about r naught? So what is this particular clear हो ना?
सर ये जो फर्स्ट psi r naught माइनस किया है वो फर्स्ट psi r naught क्या था?
This is something like e to the power I k z. हम लोग अभी इस पर बात करेंगे. Okay.
Okay. Yes.
Incoming wave as well as scattered wave. है ना? We will just try to talk about this thing separately. And what is basic assumption behind that? That incoming wave is not going to change after interaction. So whatever incoming wave inside, that will be also outside. So you can use this thing at z naught or r naught, something like this. We will discuss it later. That will be the next part of this particular integration. But can you understand all this concept? Yes. So where is the approximation? The approximation is exactly here. Look at, what is this approximation? We can write r minus r naught. This is your approximation. And we can write r minus r naught whole square as mod r square plus r naught square minus 2 r naught dot r. है ना? And this is your r. What I can do, I can take r naught square, and this is magnitude. So this is 1 plus r naught square upon r square minus 2 r naught dot r by r is there. And approximation is that this value is very big. Sorry, this value is very small. R, look at, this is your r naught and this is your r. So you can compare this thing. So what I can do, I can write this value r minus r naught whole square as r naught, sorry, r square, and this is magnitude, -2 r cap dot r naught, है ना? r by r mod r is nothing but the unit vector r naught, sorry unit vector r cap. लिख सकते हैं ना?
यस सर।
You can just write this is approximation, और ये आपको थोड़ा सा अपने ऊपर इसे डाइजेस्ट करना होगा।
सर
हाँ बोलिए।
सर वो जो डी क्यूब आर नॉट आपने लिखा है उसमें का तो 4 पाई और 4 पाई कैंसिल हो गया ना, तो सिर्फ डी डी ही आएगा ना
डी क्यूब आर वेक्टर, अभी कुछ भी कैंसिल नहीं हुआ है। ओके
सर, क्योंकि ग्रीन्स फंक्शन के नीचे 4 पाई
हाँ
भी
4
था।
पाई है तो वो 4 पाई रहेगा, दैट विल बी 4 पाई इज देयर। ओके 4 पाई इज देयर, ओके 4 पाई इज देयर, डोंट वरी, ठीक है। सो दिस विल बी 2 पाई स्क्वायर। ओके यस, ग्रीन फंक्शन का 4 पाई रहेगा। अभी मैंने इसको कुछ भी ओपन नहीं किया है। ओके आई विल ओपन इट इन द लास्ट। इसी कारण बार बार यहां मैं वेक्टर ना भी दूं, अगर क्यूब दूं दैट मींस sin थीटा cos phi everything is there. Okay, and if I am talking about r naught, I am just talking about inside. Look at, I have included potential in my calculation. This is the real challenge. Are you getting this thing? अभी तक हम पोटेंशियल को इंक्लूड नहीं कर पा रहे थे अपने कैलकुलेशन के अंदर। So we are just going to write this particular thing. Okay, so what will happen? Mod r minus r naught is can be written as r, and we have this but sorry ये तो
सर आर स्क्वायर था वो नीचे से, आर वेक्टर बाय आर स्क्वायर होगा ना सर, वो कॉमनली आर स्क्वायर।
कौन सा?
सर जो आर कैप किया है हमने,
this by r square, yes this by r square. Okay this by r square. So look, एक मिनट रुक जाओ। So what we can do, so I can write this vector as so this vector as r minus r naught whole square as r square 1 plus r naught square minus 2 r naught by 1 r and r cap. अब तो सही है ना? ठीक है?
यस सर।
Okay, so what I can do, I can, if we are doing this square part, then what will happen? I can take this thing as r and 1 plus, and this thing I can neglect, 1 minus 2 r naught dot r cap by r to the power half. ये होगा ना? Yes,
यस सर।
I can use this particular thing. So is that correct? ठीक है ये? One minus 2 r naught dot r cap by r. So this is my all approximation. So this will be r, and I can just write this particular thing. So again we can do this particular half का ये कर सकते हैं ना? Yes?
Yes, binomial
Yes,
expansion.
Binomial expansion कर सकते हैं. Then what will happen? R naught will cancel out. Sorry, half and half will cancel out. First term में only रखना है. Okay? And we have basically this particular thing as I can have r after doing binomial expression. This can be written as r minus this 2 will also cancel out. This r will also cancel out. So this value can be r cap dot r naught. लिख सकते हैं इसे approximately equal to. This is high approximation, high level of approximation we have done here. लिख सकते हैं ना? Okay. So let's try to write this equation after approximating this thing. So this is very interesting. Now, यहाँ तक clear है ये?
यस सर।
है ना? And this is all about bond first order approximation. Why? Because we are going up to first order. So this is known as first order approximation for the bond. Now look at here. And the next part you have to digest. Okay. This is very important. E to the power I k r minus r naught can be written as e to the power I k r minus r cap. ऐसा लिख सकते क्या? लिख सकते ना? And this value is e to the power I kr into e to the power minus I k r cap dot r naught. लिख सकते हैं इसे?
Yes, sir.
Now this kr, I am just putting this kr as my capital K. This is capital K vector. This K is some scalar quantity. Okay, this is root under 2me upon h cut square. But if I am talking about K in r cap direction, this is K vector, and this is identified as scattering wave vector, because this is scattered in arc. And what is magnitude of this K? Is exactly same as root under 2me upon h cut square, isn't it?
Yes, sir.
Okay. And the second part is that r minus r naught we can approximately write as only r, because due to this fact, this r is very, very large. I am just talking about distance here. I am not talking about function here. I am just talking about distance. So I have taken for the numerator is this particular r. Obviously, your question should be there, sir. Why not you are taking this much also? Because this is not needed actually. If I will take this one, this will not alter the solution sufficiently, and it will again make the thing very complex. And we also know that my scattered wave is something e to the power I kr by r kind of thing. Are you getting my point? यहाँ तक clear है?
Yes, sir.
Now look at what we have done. We have done a tremendous job. If you are going to accept this particular approximation, and this is nothing but the Taylor approximation, I am not doing something very big, but yes, I have taken this thing completely here, but here I have just taken the distance, and we know that this distance is very small and this is very bigger, so I can say this is equivalent to this one. Are you getting my point? So why we have taken this particular thing. Now look at what is going to happen here. So I need all this thing. So I will write all this thing here. We have psi r as psi naught or psi r naught right now in this time. And we have minus. Now look at this integration is only for r naught. So what I can do, I can take this part e to the power I kr by r outside this integration, isn't it? Because this integration is only for r naught. So what I can do, I can take e to the power I kr upon r, and you can take this thing as plus, and here minus m upon 2 pi h cut square, and we are just taking integration of e to the power, and this will be minus k dot r naught, k dot r naught, and here we have v r naught, and here we have psi r naught, and we have d cube r. Are you getting this thing? And what is this particular thing? If you are going to, if I am recognizing this thing as e to the power I kz, if I am recognizing this is incoming wave e to the power I kz, then what is this particular thing? Can you recognize this particular thing?
F
That
theta.
is
F theta, yes. This is actually F theta. And now you can see F theta have this particular potential inside your calculation. So let's go for, we have recognized this particular integral as my F theta. So what is my F theta? My F theta is minus m upon 2 pi h cut square e to the power minus k dot r naught v r naught psi r naught d cube r naught, and this is r naught, not r, this is r naught. So this is my F theta. And now the whole challenge is that, and this k vector you is the scattered vector, okay? The whole challenge is that how we can write psi r naught, and this is nothing but incoming wave. So here is assumption that incoming wave is not going to alter. There is incoming wave always, and after then there is a scattered wave is there. So incoming wave and a scattered wave will make the superposition and you give the complete solution. So again we have to make little bit next tricks, and this is very interesting. We can write psi r naught as equivalent to e to the power I kz, and hence it is not going to altered. I can write e to the power I kz naught. Hence it is not going to altered, and hence it is, I can write this z naught as e to the power I kr cos theta naught, r naught cos theta naught. लिख सकते ना? And this k and cos theta naught have some another number. So I can write this thing as e to the power I new wave vector k dash dot r naught. लिख सकते ना ऐसा? And yes, magnitude of k dash is also k, don't worry. Because from the cos theta nothing is going to happen. This is just an argument. So we have k dash dot r naught here. So I can write this psi r naught here, and this is e to the power I kz, so nothing to do with this. I have to just put psi I k dash r naught is something like this. So should I put it here? So what is my F theta? And now we get the answer. Minus m upon 2 pi h cut square e to the power I k dash minus k dot r naught v r naught d cube r naught. Okay, and I can put k dash minus k as some q vector, Look at here. This is my k dash vector. This is my k vector. And this is my q vector. And this q vector is k dash minus k. Okay. And this angle is identified as some theta. This angle is identified as some theta. Up to that, are you people comfortable? So now we can have approximation. The first approximation is if my energy is very low and there is very few momentum is going to transfer. And please, momentum is not only going to transfer when you are changing the magnitude. If you are changing the direction, then also momentum is going to transfer. Are you people comfortable?
Yes, sir.
Momentum is a vector quantity. Suppose something is going here and from same magnitude it is going into this direction, then also your momentum is going to transfer. So first case, we have the case for the very less energy or very small energy, we can have this particular thing. So for low energy, when momentum transfer is almost zero, momentum transfer is almost zero, then I can have this value is approximately 0. So there is not any momentum transfer. So this value will gone, and we have f theta as minus m upon 2 pi h cut square, and this value is v r naught d cube r naught. And now every r is gone, only we have r naught, so we can write it in a generalized form. And what will be this generalized form? That will be minus m upon 2 pi h cut square vr, and d cube r is r square sine theta d theta d phi. This is your f theta for the low energy. Now look at how simple it is, isn't it? Are you getting this one? And this is the formula, is the final outcome. Are you going to appreciate this one? Okay.
Yes.
Huh? So this is your energy for the, sorry, this is for f theta for the low value of energy. And next, in the next class, just it will take 5 minutes, we will also discuss for the high value of energy for the spherical symmetric system. You can solve it for the non-spherical symmetric system when potential can be function of theta also, the bond approximation can be used. Okay. So next class, we will just complete just 5-minute theory, and then we will apply this thing to calculate the differential scattering cross section and all this thing. And you will verify that your answer will be exactly match with your basically experimental result of all Rutherford scattering and all kind of thing. So if it is going to verify this, the result of the experimental facts, then obviously my theory, my approximation is going in good direction, isn't it?
Yes, sir.
So if you have any doubt, you can ask me. Next class, we will just go for different types of problems. So look at how simple is this equation, isn't it? Nahin? Actual
Yes,
challenge is to calculate this particular f theta, and you have calculated this particular f theta. Obviously for the low value of energy. For the high value of energy, there is little bit of more complication, but yes, that is also workable if you know this particular f theta. In general, people, what people do, they just remember this formula and they just continue to do the working thing. But yes, how you are getting this particular formula is very important. Then only conceptually attack the problem. Otherwise, it will be very difficult that where you should use the formula or where you should not use formula. Okay, and we will see how this picture will very important one into the next class. Any doubt?
सर 5 ही तो आ गया सर, ये
क्या आ गया?
सर f थीटा 5 हो गया ना सर अभी.
सॉरी, समझ में नहीं आ रहा. हाँ, f थीटा तो डिफरेंस से इंटीग्रेट करोगे ना. दिस इज ओनली फॉर r, है ना.
यस सर.
सो इंटीग्रेट करोगे 2 पाई आ जाएगा. सो देयर इज नॉट एनी प्रॉब्लम. अगर r थीटा 5 भी है तो फिर इंटीग्रेट करो. इसी कारण तो इसको अंदर रखा ना.
Yes sir.
You can just put v as a function of r. It can be function of theta also, don't worry, but it should be integrable. Okay.
Okay sir.
So now this is very compact equation, isn't it?
Yes sir.
And it is very compact equation. And look at what you have done. अगर आप पूरे के पूरे equation को देखो, then आपने क्या किया है कि टेलर एक्सपेंशन को कितना ब्यूटीफुली आप यूज किए हो। आर यू गोइंग टू अंडरस्टैंड दिस थिंग और नॉट, है ना? ओके, सो आज के लिए इतना ही रहने देते हैं, अगर कोई डाउट हो तो पूछ सकते हो।